Okay. Okay, so we are ready to go then. So yeah.
Yes, you may
Okay.
begin.
Yeah, thanks, Crystal. So hi everyone, and first of all, thanks to Formula Bharat for arranging this event. Had it been great if it was a live event. So my name is Veer Alakshendra, and I'm from MathWorks. So I work with the worldwide student competition teams, and along with me, I have Stephen from Veloz Racing. So today we are going to present something using MATLAB apps. So even though we have mentioned that MATLAB apps can be used for Formula Student competitions, but yes, I mean this is because this was done because I mean you all are from the Formula Student competition, and we will show you some examples from regarding to automotive, but still, like if you have any other applications, you can use the app. So before I move to the agenda and start the presentation today, I'll just pass on the ball to Stephen. Stephen, if you can introduce yourself. And we are really excited to have you here because you're going to show some really cool and something real stuff, which is very much relevant to the student teams. So over to you, Stephen.
Thanks, Veer. Hello, everyone. My name is Stephen Ninan. I have been, like all of you, I mean, I've been in Formula student for around 2.5 years, and I was part of Veloz Racing. In my first year, I worked in the brakes subsystem, and then later on, I moved on to vehicle dynamics, and in that, I ended up working with tire modeling. So I'll be happy to share my experience of working with MATLAB and using it as a tool for tire modeling.
Awesome. Awesome. Yeah, Stephen. Thanks again, and thanks for joining, Stephen. So I think all of you must be motivated now that we have a very nice speaker which is coming from your community, and he has used the tool for some uh, interesting thing, because tire data handling or tire modeling is a very complex thing. And so I think it will be interested to all of you. So today's agenda, what we are going to see today is I'll just introduce you what MATLAB app designer is. Then we'll take some demos. So I'll be taking very simple demo because we have to just create a simple app of data smoothing app. And then we'll check out one role center calculator app as well. And then I'll hand it over to Stephen. Stephen will explain the his tire data handling tool, and then we'll take the questions. And finally, we have very interesting program at MathWorks now. It's called MathWorks Excellence in Innovation Program. So I'll give an overview of that. So yeah, stay connected. So a lot of things, I mean, a lot of interesting things coming up. And I assure you that whatever we show you, that will be somehow it will be relevant to your competitions. So yeah, so now talking about apps. Now we have been like seeing apps everywhere nowadays. I mean, whether you want to have a want to see your daily step count, calories count, if you're like very uh, uh, fitness freak, or even if you want to do some kind of technical things, like for example, we are continuously talking about the tire modeling app. So what we already have generally is, for example, we have some data. It could be engineering data, like it could be your tire data from the tire consortium, or it can be some data which you have collected from your hardware. For example, if you have your data for the your vehicle position, velocity, acceleration, then further what you want to do is that if you have the data, first of all, you would like to visualize it. I mean, visualize it because it will give you a better understanding. For example, if it's a 2D plot, you would like to visualize it and understand that, okay, how is the velocity changing with time? Then there are statistical methods. Then you also want to explore with pre-built algorithms. Now, giving an example of pre-built algorithms could be like, for example, you collected some data from the sensor, which is very noisy. But what you want to do, you want to filter out, okay, or you want to smooth it out. So that is, I mean, where you can use these apps. Another thing is like the best example what we are going to show today is from Stephen, like how he developed his own algorithm based on optimization to make that tire handling tool. So similarly, you can also have your own algorithms in the app and build your own solutions. Now, like if you have all this, now another thing which is really important is that you want to share it. Now, give an example, like Stephen has made an app for tire handling. Now, if there's some team member who is part of powertrain team and he or she wants to use that data which has been extracted from that app, so now that doesn't mean that again the powertrain guy will call the vehicle dynamics guy that, okay, can you come here, I have some data, I just want to check the algorithm, build some algorithm and see how what are the coefficients of tire, because that could be needed in the powertrain design when he or she is performing a full vehicle simulation. So rather than that, what Stephen can do is, like, I think Stephen has already done that, that he has created an app, and it can be like on the web, it can be directly installed on MATLAB, or it can be also shared as an exe file where you don't need MATLAB, such that if you have that app, you can just share with a concerned person from the powertrain department, and he or she can input the data and analyze and get the output without getting deeper into the tire modeling concepts, because the person's focus is on the powertrain design. So as said, s- application sharing, so that's the most, I would say, one of the advantages of MATLAB apps, that you can share it in any form, whether web app or MATLAB app, or if the person doesn't have a MATLAB, then also you can install in your system. So now, what is MATLAB app? It's, I mean, nothing special. It's just an app. Now, what MathWorks provides you, it provides you a design environment, in the sense that if you have a canvas, you can just drag and drop the knobs, the sliders, the plots, and then when you, I mean, we will see the whole procedure when we open the MATLAB app, such that already the object has been created for all those knobs or the all the component from the library, and then you can have your own functions in the app for performing different algorithms. Now, I mean, you can see on the screen that also on the third point specifically, we have mentioned object-based code format. Now, if I'm not wrong, a lot of you, I mean, must be scared with the fact that is this is object-oriented programming. But don't worry. Even I am not like very, I mean, good in object-oriented programming, because a lot of people get scared. So I'll show you what it means and how it is done. And yeah, I mean, we already spoke about that you can use the app and create and share it with your team members. So with this, giving an overview, so what we are going to see as a first demo, a very basic demo, is this, that we have a noisy data. So this is basically like if you're performing, um, uh, for example, closed loop simulations involving both longitudinal and lateral vehicle dynamics. So what you need as a reference point, you need the yaw, the theta, that is, okay, your signal, reference your signal, then x and y position, reference position, and also the velocity. So this what you see is a position data collected from the sensor, which is very noisy what you see. And our aim is to build an app, a very simple app, such that we can smooth this data. So let's do one thing without wasting time. Now, since you understand that we have a data and we want to smooth that data, or we want to kind of filter that data, so what we'll do is we'll switch to MATLAB and we'll start building this simple, what do you say, simple, very simple data smoothing app. So this is MATLAB 2021A, and apps are also available in the previous versions. So what we'll do is I'm not going to go through the whole canvas, MATLAB canvas. So if you want to create an app, what you need to do is you press on the new over here. One second. Okay, yeah. And then you have options for app. So you click this app, And once you click this, so this is what you get as a app designer page. Now if you see over here, so it already has some default layouts. It has blank app, it has two panel app with auto reflow, it has examples, also different examples. So I mean, based on your application, you can design the layout of your app. But for the time being, let's do one thing, that we'll use the MATLAB, the blank app. So now this is the canvas. So in the canvas, what you see over here, you have different libraries. Okay, and there are, I mean, the in the top ribbon you have different things. We'll talk about this later, but you can see that there are different libraries. Now I think if you remember, this is what we are trying to build. Now if you see, there are different components in this app, which are, this is your what do you say, access, then you have slider, you have some push buttons. So what you can do is that you can just drag and drop. It's very simple. So you can just drag and drop this axis, and then you can select the size, and if you want to crop and resize it, you can do that. Now when I just imported it over here, okay, drag it over here, what you can see is that it has already created app.ua axis, which is basically denoting this axis. And along with that, you also have options for uh, string, labeling the X label and the Y label, Z label. Then you also have options for font size. So you don't have to code anything over here. You can just simply like select it over here that, okay, I want some different font size, and even X tick and maximum, minimum limits and everything. You can have it over here. Now, what we'll do is, so once you drag any of the components, when you go to the code view, you can see that there's already one class created for this, and along with the properties. So basically, properties are coming from the figure and the or you can say the properties are defined for the figure and the axis, and the object name is basically this is the class which has been created. And you can see that this all, I mean, lines of code, this has been automatically generated, just, I mean, dragging and dropping to the canvas. Now moving ahead, I mean, let's add other components. What are the other components? We'll have a slider. So let me search for that. So here is the slider. Okay, and you can also change the maximum minimum values of the slider. Further, you have this push button. So we'll have two push buttons because one is for load and one for exporting the smooth data. So I'll name it something as load, and this as, okay, did I delete that? Yes, it got deleted. I'll name it as export. Now when you go to the code part, you'll see that already, I mean, all the properties have been defined for the figure, for the export button, load button, slider level, and everything. Okay, so now what we need to do is, so basically it's an object, okay, which is comprising of properties. Properties are defined over here, and functions. Now functions are over here. You can see these functions are defined. However, you haven't defined that what the load button has to do, or what the export button has to do, or what the slider has to do. So let's get into this load button, and then write a set of very simple commands so that it can load the data which is already there. So what data do we have? We have this data. So so this is saved uh, in my directory, and these are the two data, basically distance versus y reference. Okay, so okay, so now what I'll do is I'll get back now. Since you understand what data we are using, we'll just write, I mean, click on code, and then, so over here, when you let me zoom it so that you can properly see. Okay, so you can see that these are the different apps which has been mentioned with different names. So what we need to do is in the load button, we need to add some function. So what we'll do, we'll click on this, right click, and then call back, and then add button pushed function callback. Okay, so what it will do, it will create space for writing the function. So here what we have to do is we have to load the data. So for what I'll do is s, okay, let me, yeah, okay, yeah, 1 second. Yeah, so I'll just load the data. So for loading the data, so the command is basically load, and then I'll simply say uh, the name of the folder, the file that is, and you can also see, let me zoom it. You can also see it is already giving you some of the options, which means like this is smart selection. So what do we want? We want this app data.mat. Okay, so I'll just do it over here. Okay, there's some issue with pilot using two screens, not a problem. Further, we want to plot it. Okay, so plot, and then the data. Now let me show you. I mean, let me show something. Those who are not new to MATLAB, they will easily understand what we are doing. So if I load this in the command window and press enter, so what happens, this value comes as a structure. You can see over here, it's a structure, right? And then inside this structure, you have these two values, that is distance and the yref. Okay, so how to call these values? It is s dot distance and s dot yref. So I'll do the same over there. So s dot stpp comma s dot yref. Okay, so now let me run this app. Let's see what happens. I'll run this. Okay, let me save this once. Okay, yeah. So here's the app. And I see that, I mean, the app has been created, but let's see if the load button is working or not. So I'll load this. So what happens over here, we were expecting that the plot should come here, but rather than that, there is some extra figure that has been created. Okay, so it means that it is not getting connected. The command lines are not getting connected or not connecting to this, what do you say, the axis, the UI axis. Okay, so in that case, what you need to, the reason why it is there, because you see here it is a UI axis, so we want to put it, I mean the plot in that, so we have to define that property. So app dot UI axis comma, so now what would happen is you can see the plot app.ui axis. Why we have written, because that's a property. I mean that is because we want the plot on that canvas, and then we have these values for the distance and the reference y position. So I'll just again, so now let me again run this app. Let's see what happens. Okay, so now you see over here, okay, we have the canvas. Let's see if what happens if we press the load button. Okay, now you can see that the load button is over here. Okay, so now the first task has been achieved, that we have the data loaded on the app. Now further, what we want to smooth the data. Now to smooth the data, the built-in function in MATLAB is called smooth. Okay, and then you have to define the yref, the data points that you want to smooth, and along with that, there's some coefficients that you have to define. Now, once you have this load data, another thing is that we want the slider. In the slider, we want that when we move the slider, it should smooth the data. So for that, what we will do is, in the option, we will in the callbacks. Now we have to again add the callback function. So it has two options: add value change function callback, and it has another that is add value changing function callback. Now since we want that when we move the slider, it should smooth the data, so we'll just take this add value changing function callback. Okay, and now the the built-in command in MATLAB is smooth. Now the problem with this is that we have defined the data in this function. Okay, it is over here, the distance and the uh, and the y reference value. But how to communicate between this, or how to bring that value also in the function? So for that, what we do is we need to define the property, so that when we define the property for the data, so any function if we use, it will be connected to that. So I'll show you what I'm talking about. So I'll just click on this add, and I'll just name. So one is dst distance, and we have this yref. So let's keep the name shorter, and distance and yref. And further, what I'll do is over here that I'll define these values. So the value would be app dot dist is equal to, so first is this value, control V, and then another would be app dot yref is equal to s dot yref. So here is some typo, so that it will be p, and okay. So now, I mean, what I'm doing is I have defined the properties, so that, I mean, defined the data as a inside the property, so that, I mean, it can be used anywhere in all the other callback functions. And further, what I'll do is now, if I go to this, now this is the place where we need to define the data. So what I'll do is I'll just define a variable. Okay, whenever I'm using two screens, there's some problem with Zoom. Not a problem. Okay, smooth data is equal to, now the built-in function name is smooth, and this will be in between the, now here the thing is, I mean, let me show you something. I mean, don't worry that you have to uh, remember all the functions. Basically, you can, if you just simply type smooth MATLAB function, if you just simply type this, so what happens, it will get you to that function. And what are the arguments required for this? This has been explained over here. Okay, so you can see that one of the most basic one is this smooth y, means y is the argument, that is the data, that is, in this case, it is the yref. Okay, so that is what we are doing. So this so you can simply, like, I mean, it is not possible that you'll remember all the built-in functions. You can simply do a Google search and you'll get that. Okay, now smooth, and here what we want to smooth is, we want to smooth the data. Now we won't write yref, because we'll write app.yref, because that has been defined as a property in this app. So we'll write app.yref, comma, changing value. Changing value is the value for the slider. Okay, and then we'll have like all those commands for the plotting. So I'll just copy and paste. I want to waste a lot of time over here, and I'll also, okay, so that has been done. Okay, so now what I'll do is I'll again run the app. Let's see what happens. Okay, so again we have the canvas, we load the data. Now let's see if it works or not. Okay, now you can see that it is working. You can smooth the data, right? So here you go. So this is the app which we have built just for smoothing the data. Because if you're collecting data from sensors, I mean, chances are it will. I mean, there will be a lot of noise. So you need to like filter out that data. So this was just a very simple demonstration of building apps in MATLAB. Now, once you have the app built, what you can do is when you see over here share. Now, what are the different forms in which you can share? You can share it as a MATLAB app. You can share it as web app or as a standalone desktop app like creating an exe. So if you click on this, you don't have to do anything. You just need to, where is that page? Yeah, it is on the second screen. Yeah. So there's a compiler. You need to provide certain information and then you have to package it. Okay. So this is how you can share with those students or your team members those who are not even having MATLAB. They can simply install it as an app on their desktop. Perfect. So I hope you got an idea. There are a lot of resources to learn how to use MATLAB apps very easy. Okay, I mean nothing like very difficult. And then further, what I'll also show is something a bit complex, a next level thing before we move to the tire modeling one is the role center calculator app. Now again, if we go to this app, so what it does, this is again a very simple app. Basically what it does is it just calculates the roll center based on the track width and the wheel radius and all the other components. I mean all the other parameters which are needed for calculating the roll center. Okay, so this is the UI, what it looks like. And again, if you go to the code view, you can see that all the gray portion, basically, these are all like by default, you can't change that. These are all the properties. And further, this is the white, I mean, side where you can see the color white, where you can have your own functions and you can edit that. So these are all basically containing all the equations, I mean, which are needed for calculating the roll center and as well as kind of drawing some nice plots. So let me run this again. So what it does is that it opens like this and it has the value. So you can visualize it. So, and it also gives this. So this is a roll center calculator value. And then further, you can simply change the track width. And again, you can click on the result button and this is how it works. So very simple. I would say like this is just for motivating you, but you can make more complex apps and you can share with your team members. Okay, and one last thing before giving it to Stephen, I also shared that said that you can also create MATLAB apps. So we created MATLAB app for this. So what happens is you can add it in the app section of the MATLAB. So you can see that these are all my apps. So one of which is a roll center calculator. So this also you can just you can create your own app and you can add in the MATLAB app section. So yeah, I would say this was a motivation. I mean, for you to build apps and also a very basic steps. We have shown you that how you can build an app and also how you can package it and also how you can share with your team members. So with this, what I'll do is I'll stop sharing and I'll pass the ball to Stephen. And Stephen, over to you. And yeah, I like your background. That's nice.
Um, yeah, am I audible?
Yeah, you're audible.
Okay, let me just share my screen and is my screen visible?
Yeah, yeah.
Okay. Um, so yeah, good evening, everyone. It's very nice to be able to share my experience of developing using the MATLAB app designer to develop a time modeling tool. So let's begin. So before going forward, a small intro to about of my team. So we are a Formula student team from VIT Pune, Vishwakarma Institute of Technology, Pune. We started in 2011, and since then we have built 9 prototypes. And our most recent, I mean, our best position in Formula Bharat was in 2020, where we achieved second place overall and also a third place in engineering design. And our most recent prototype is the VR19, which you can see on the image um, on the right. Moving forward, so uh, to begin with, I would like to explain what was the motivation for making this app. So um, the tire is basically is the only part of the vehicle which is in contact with the road. So even though if you say that the brakes are responsible for generating your stopping force, or your engine and transmission is responsible for generating acceleration, but at the end of the day it's the tire that actually produces those forces, and which is transmitted backwards through your suspension, and then your vehicle moves or slows down or whatever. So it therefore becomes important to understand how your tires will behave in different conditions. And and if you have a better we realize that if you have a better understanding of the behavior of tires, you can design your car around your tires. So because your tire um, is the limitation, or like you can have a great transmission, but if your tire is, I mean, for example, if your tire is not if your tire is not able to produce uh, the force, like for example if your torque is too high, and in the acceleration case you'll just have wheel slip, and you won't be able to extract the perfect uh, time in your axi run. So therefore we realized that this was an important aspect we wanted to work on. So it's basically a tool which we designed to help us understand the behavior of the tires we were using, and to better design our cars around those tires. So if you're not already aware, but FSA has FSA TTC. You can has a it's a forum where they have provided tire testing data for Formula student. So it's called as a tire testing consortium, and your team can sign up and take up membership there, and you can get, it's a one-time fee, and you can get access to all of the tire data, all of the tire tests. And it's an active process. They do tire testing in different rounds. So once you take membership, you get access to all of the data from all of the rounds. So I recommend, if you are not already a member over there, I recommend you to take membership over there, so you can get access to tire data for all of the possible tires for FSA. So moving on, I'm explaining about how or what is the methodology that we have used. So basically, the tire data which you get from TTC is, it's basically a CSV file, and it contains uh, it's basically a log of all the measurements which were recorded during the tire testing run. So these include the forces, the pressure, the speed at which the tire was running at, the um, camber, or in terms of in the tire testing procedure, camber is referred to as inclination angle, because camber is with respect to the vehicle, and then other such parameters. So if you want to make sense of this data, you need to first sort out the data, for example, on the basis of normal load, because we know that your grip will vary as a function of the normal load. So therefore, you need to be able to group your data into the different normal loads that were tested, because it's not possible for the during testing to have all the normal loads tested. They test it at different load steps. So for example, they'll test it at 200 Newton, then 400, then 600, and then 800, and then 1000. So yeah, and that depends upon the run, the procedure that was used. So um, once you get access to this data, you'll have to sort it out, and then you can group it. So once you group it and sort it, what you will see is the figure on the left. And um, as you can see, I mean, you can use this as a preliminary way of understanding your tires. You get a rough curve, but you can clearly see that there is quite a bit of noise, as well as one main drawback over here is that, as you can clearly see, the loads are in steps. There is 200, then 400, then 600. But what if you wanted to do a simulation and you wanted to find out how much grip am I having, or how much lateral force is my tire generating for a normal load of, say, maybe 250 or 300, somewhere in between? How would you calculate the grip from in those conditions? So basically, the what for these situations, what is commonly used in the uh, uh, vehicle, or you can say tire industry, is what is called as a tire model. So tire models, there are different kinds and different, uh, I mean, there's a lot of research in that area, but a very commonly used tire model is the Magic Formula tire model, or the Paseka tire model. So it allows you to fit your, I mean, basically what you do is you try to estimate coefficients for the tire model, and then once you do that, you can calculate the you can kind of estimate the grip or the forces generated by the tire in conditions which you have not tested, and it tends to follow the general pattern that we have observed in the data. So so first step in my application is we start off with the data sorting. That is, we load the tire data file, and then we sort it into based on a number of parameters. To name a few, we have normal load, we have inclination angle, the tire pressure, also the speed, because speed also has an effect on the behavior of the tire. And then, yeah, so we group the data based on that. And then the second step after that is collapsing. So basically, on the left, you can see that there is, even after sorting, there is a considerable amount of noise. So to better uh, to help better in the fitting process, what we do is we collapse the data. Which, and by collapsing, we mean is, on the extreme right figure, you can see there is these black lines. So instead of using the data directly for fitting, we use uh, smooth polynomial equations, which will uh, which approximate the tire data curve, and then we fit the magic formula tire model to those um, curves which we have fitted to the raw data. So this is what is uh, we refer to as collapsing. So so this is the raw data which you get, and then the second step first step is tire data sorting. Once you sort it, you get the figure on the middle, that is the sorted data. It's better grouped together, but still there is large number of data points, as well as a bit amount of noise. And also, as you can see towards the center, there is hysteresis. So to deal with these problems, what we do is collapsing, where we fit one polynomial curve to each of the tire data curves. Yeah. So the black line represents uh, the the fitted curve, and then the sorted data. So moving on, this is a screenshot of my application. So as I explained earlier, my app is divided into three steps, the same steps which I mentioned in my last slide. So one tab for each step, and yeah, I'll be showing a demonstration following this presentation, so you can understand better. So yeah, moving forward is the use cases. So the use cases is, I mean, there's a huge scope for applying this in any part of your vehicle design process. You can use this, the transmission team can use this, the brakes team can use this for designing the brakes. You can use it for load case simulation, for your suspension links. You can use it for lap time simulation and whatnot. So just to give an example, I've given two use cases. On the left is uh, once you have fitted your model, you can simulate the tire behavior as a function of the inclination angle or camber. So you want to know how your tire is affected by camber so that you can make a good decision while setting up your car, for example. So on the left, we have the figure of what the figure is you can see the title on the top. It's effect of camber on lateral force. So this is one constant normal load, that is the normal load on the tire, and the slip angle is also constant, which is 10 degrees. And what I'm doing is I'm varying the camber. So on the x-axis we have camber, and we can see that as you are increasing the camber for this particular tire, it is tending to produce less lateral force, that is less grip. So this would suggest that a zero camber would be a best target design for this tire if you're using this tire. And so that is one application or one use case. And a second use case would be on the right. Once you fit the tire model completely, you can even plot the traction circle. So which is a plot of, so on the x-axis you have the longitudinal force, and on the y-axis you have lateral force. So basically this gives helps you understand that in combined conditions, that is basically whenever your car is running on the track, you're never doing pure cornering or pure acceleration or deceleration. It's always a combination of both. So in these combined cases, your tire will produce less grip in both directions because your force is divided, right? So this traction circle will help you understand, and I mean you can use this for your lap time simulations and yeah, number of use cases of this again. So yeah, so this is an again an important uh, thing you can use this application for.
And Stephen,
So
just to add that one thing, the app what you have built, it can be also like used like what you have plotted between lateral force and camber angle and longitudinal force and lateral force. So, I mean, when the students are also doing some kind of lap time simulation, or you can say full vehicle simulation, in
yeah,
that case also, if they're designing the full vehicle simulation, these can be used as a lookup table, whichever, like whether it is a MATLAB function or some other I would say program,
yeah,
or
yeah,
even if they're using Simulink, they can use it as a lookup table. So yeah, I think this is like super useful. Okay, yeah,
yes.
yeah, we can go ahead.
Okay, so next I'm going to be showing a short demo or demonstration of my app as it runs. So let's begin. So I've already loaded my application here. So uh, I'll be showing and I'll be going through the entire steps of how my application works, and so you can better understand. So the first step, you start with pure. So and first you have to load the tire data file. So I'm going to load one tire data file as an example. Let's select this one, or maybe this one. Okay, so I'm opening it, and yeah, 1 second. So if we see here, once you open the file, what it is plotting in the blue here is it's a plot of basically what all is there in the file. So it's plotting velocity versus time, normal load versus time, inclination angle or camber versus time. At the bottom left, we have slip angle versus time. Then the middle one is slip ratio versus time, and again pressure versus time. So this file which I've loaded right now is a pure cornering case. So therefore the slip ratio is always 0. And as you can see, the slip angle is varied between 0 to 15 degrees. And also the inclination angle, that is the camber, is varied between 0 to 4. Yeah, 0, 2, and 4 in these discrete steps. So my app here, I've designed it such a way that you can have uh, basically you can give it the normal loads. So basically you can look up in this figure, you can find out what normal loads are there, and then you can pass those as arguments to uh, this application. And then Similarly, for inclination angle, for tire pressure, you can check over here, what is the tire pressure? Okay, it's maybe around 82. So I can give that value over here. And then also a certain tolerance. So it will consider maybe 5 psi above and below 82. Same for velocity. And also sometimes there are these periods in which there is no useful data. So you can filter that out. So for that, we have that time period neglected. And also I've given an additional option for automatically removing outliers. So once you load the data and you give your conditions, what you want to filter out, you just say sort, and then it sorts out the data according to conditions you have passed, and then it says sorting is completed. If you wanted to see the sorted data, you can just say plot sorted data, and it should give you a plot. Yeah. So this is the plotted data. On the top, we have lateral force, and at the bottom, we have self-aligning torque. So yeah, this is the sorted data. And if you want, you can even, we have added functionality that you can save the file as an Excel, which you maybe might want to pass on to some other subsystem if they wanted to use it. Then next, I will be loading the combined data file. So that one is over here. And the same steps for combined data, you given what all loads you want to consider, what all inclination angles you want to consider, and all those parameters. And then you just say sort, and it's sorted is completed. Again, to plot that one, and we have the plot here of, this is, I think, yeah, this is longitudinal force on the x-axis, and this is slip ratio. So for different inclination angles, yeah, this is the sorted data. Same thing, it is plotting, this I guess is combined lateral force versus slip ratio. Okay, and
Stephen,
last,
just a question. Even I think if students might be asking,
yep.
I can see that like the data what is now after sorting out, it's
Hmm.
very like current like clean. So like did you like remove the noise out of this using some functions, or
No, I've not used any special
not?
functions over here. I
Okay,
mean,
okay,
just grouped it based on these
okay. You have grouped it
categories.
now.
Yeah.
Okay,
So
okay,
if you
okay,
find more noise, you can just adjust the tolerance over here. For example,
okay,
here
okay.
FZ tolerance is given. You can
Mm-hmm.
reduce the tolerance, and then yeah, the noisiness will decrease.
Okay, okay,
Yeah.
okay. Great,
So
great.
that's the, yeah,
Okay, so
that's the
that
parameter.
tolerance is the
Yeah.
parameter which
Yeah.
can make the data
We
plot.
can tune
Okay,
it. Yeah.
fine. Okay, okay, awesome.
Next, moving on, we have, so we've loaded the data. That is the first step, sorting. Next, we move on to compression. So here you can just give the regions you want to consider in your model. So minimum slip angle, minimum and maximum slip angle. Similarly for longitudinal. And the step here represents the step which your algorithm is going to use. I mean, uh, the step between two consecutive values. Yeah. So once I say give those parameters, I just say compress. And yeah, so what I'm plotting over here is the R squared value, so which is a measure of the goodness of fit of my polynomial curve to the data. And I can plot that data as well. Sorry, I can plot the compressed data or collapsed data. So what you can see over here is the black line here represents my polynomial curve, which is, as you can see, it tries to approximate the data points. So this is for longitudinal force, and we can have the plots also for the other forces. Here we have lateral force. Yeah. So as you can see, it fits the data pretty well. Um, and then these black curves become the input to my uh, next step, which is used for estimating the magic formula parameters. So quickly moving forward, we go to fitting tab. And so here it's asking for inputs, which is fz0 and r0, which is the nominal load and the nominal radius. So these are parameters, or like, yeah, these are parameters of your tire model, of the magic formula tire model. So at the bottom, I've provided a description of what this means. So usually this is the highest load on which the tire has been tested. So that's what most research suggests, that you can use it. That is your nominal, and rolling radius is your basically your um, nominal radius of your tire without load. So once you give these parameters, you can begin your fitting process. Also, there are parameters like population size, maximum generations, and gradient descent loops. So this is controlling actually the internals of the fitting process. So I'll be explaining a bit about what is going on internally once I start the loop, because it takes a bit of time to fit the coefficients or the model to the data. But these parameters are actually for the genetic algorithm which is being used on the inside. So yeah, you can check up a genetic algorithm if you want, if you want to, if you don't know what all these parameters mean. So once I say fit, it starts at its fitting process. So right now, it's doing the initial fitting process. So yeah, to explain what is going behind under the hood, is that I've framed it as an optimization problem. So the black lines or the polynomial curves which we showed in my last, which I showed in the compression tab, is your true points, or your where your data is. And then what I do is, um, we estimate, we give one input of, say, some random value. For example, if you give some random values to the tire model, you take the output of the tire model and you compare it with those black curves, and you see how it is shaping up with respect to that, and then you calculate an error. And then, so you calculate the error between your data and your tire model. And then the optimization problem becomes simple, that you try to minimize that error. And as you minimize that error, the model will start to converge towards your data, and the coefficients with the minimum error would ideally be the best coefficients which describe your tire the best. So that's what's going on behind the loop. So, and what is used for minimizing this error is initially I'm using a genetic algorithm. And because normally gradient descent is used, but gradient descent requires an initial guess, and calculating the estimating the initial guess for the time model coefficients is a bit difficult, and also it's very sensitive to the initial guess. So if your initial guess is off, then your model may never converge. So I've through multiple tests, we found that genetic algorithm gives good results when it is combined with uh, your gradient descent. So genetic algorithm calculates the initial guess, and then the initial guess is passed on to the gradient descent. So right now what is going on is the gradient descent. So I'll just stop it so that we can see the results till now what have been achieved. So yeah, it gives me all the plots. So this is the pure tire model, that is pure cornering. So
So
yeah,
Stephen, the black one is the fitted data, right? The black
yes,
one.
yeah,
Okay.
yeah. So the black line represents your magic formula tire model, and the colored points are obviously your data. And on the top right, you have in this legend, you get the R squared error for each of those curves. So you can see that one is an ideal value, but yeah, you get a very, very
Yeah.
high R squared error. I mean, R squared value here. So yeah, so these are the results. And then same, so this is for 0 and 2 and 4 inclination angles.
Okay. Okay.
Yeah.
No, this is a good approach because I mean, you were talking about the initial guess. So
Right.
we already have one script based on that. I think it's based on the curve fitting algorithm, what the built-in functions what you have used. But the
Yeah.
problem with that is that the solution is not unique, and it's very like you can't rely on that solution because it is based on initial guess. And as you said,
Hmm.
getting initial guess in this kind of non-linear curve is like
Yeah,
it's like a
exactly.
mess. I mean,
Yep.
it will be difficult to converge that.
Hmm.
Okay, no, that's a good explanation of that, why you have used this approach. Okay.
Yes.
Yeah.
And I think that's my presentation. And yeah, if you want, if you are any of you is interested to find out a bit more about how the application is working or what kind of algorithm exactly we have implemented internally, you can please feel free to refer to our article. uh, I've cited it here. It's available in SAE's International Journal of Vehicle Dynamics. So yeah, if you are interested and if you want to know more, please feel free to check out that article. Yeah. Yeah, I guess that's it from my side, Veer.
Yeah, yeah, Stephen, I think it was great. I would say, I mean, like you have explained, I mean, very deeply, like why you used it and what was the procedure.
Yeah.
I kind of especially like the fact that how, I mean, the reason what you gave, why you use this approach. So, I mean, it also kind of gives me an idea, okay, why, like, initial guess part is a tricky thing, and that's why I think sometimes what happens is like even though if you're able to fit the lateral one, you'll have issues with the other one, the longitudinal one.
Yeah.
So awesome. I think, and yeah, I think I would encourage all the other teams or the students to have a look into that paper. Even I read that paper, and kind of a really nicely written paper that even they can get some idea and they can build their own app.
Yeah.
So yeah, thanks, Stephen. And again, I think when we um, join the Gather platform, there we can have more discussions if
Yep.
students are having any questions. So
Sure.
before we move to the Gather.Town and meet you all over there, so just a quick thing, wanted to share something interesting with you guys. Um, Stephen, can you confirm if you can see my screen?
Yeah, I can.
Okay, yeah, awesome, thanks. So yeah, so again, hi everyone. So we have something called as MathWorks Excellence in Innovation Project. So if you remember, and even I think when I was a student, I used to look for projects which are like industry-led projects, or which are the solutions which are being used in industries. Okay, so MathWorks recently we have started something called as MathWorks Excellence in Innovation Projects, where we have around more than 30, I think even more than 35, I guess, projects uh, for different areas, whether it is robotics or automotive or aerospace. So now let me get to this link and show you that what I'm trying to say. So this is the GitHub link over here. Okay, so this is where you'll find all the projects. Now first you can have a look into this, where it explains what is this MathWorks in excellence in innovation projects. Now one question which you all keep on asking, like what is the benefit of that? See, one benefit is that you will get a chance to work on a industry led solution and even learning MATLAB and similar ones, because the best way to learn is to do some projects, something like what Stephen did. I think now he's like a pro in making apps or using what do you say, the optimization techniques. So that's the best way you can learn any tool. And then, I mean, as you can see, we have also mentioned that even more, you gain official recognition for your problem solving skills from technology leaders at MathWorks. Okay, so this is one of the benefits of doing projects. So what happens is, like you can have a look into different projects. So these are the projects listed, and something which could be relevant to all of you is path planning for autonomous race cars. Now, although I have mentioned over here that it is autonomous race cars, but if you see, it is basically optimizing the racing line of your track, because based on that, you can minimize your lap time, or you can also train your driver that okay, when to corner, what type of curve you should take. So although you can see autonomous over here, and you might be thinking, okay, I'm not working on autonomous, but basically it is like optimizing racing lines for race cars. So it has a motivation, project description, then background material, and we have also here listed out a background material, which is a kind of like, I would say, solution already provided by one of the person on GitHub. So this is what we're talking about actually, optimizing the race lines. You can see that how is taking the corner. I mean, taking the cornering over here using this racing line. Now, what you need to do is, if you are interested, if you are willing to do this project, or any of the projects which are being listed over here. So here is the procedure to how to participate. So you need to fill out the form. So it will point you to the Microsoft Forms, and you can fill all the details and all the next steps, and then you will get an email from our end where more information will be provided, along with like what are the benefits of doing the project. Okay, so this is what I mean, like I wanted to share with you. Feel free to reach out to us with respect to if you have any queries with respect to, like, if you want to know about MathWorks excellence and innovation projects. Okay, now before moving ahead, I'll just I mean, thanks to Formula Bharat organizers that they keep I think regularly keep on sharing the resources what we share with them. So I'm not going to again go through all these resources, but rather I would first of all, if you're not a part of this MATLAB Assembling Racing Launch Facebook group, I would suggest you can join this group because we keep on adding the latest news over here regarding webinars and latest videos, blogs. For example, here also we announced, I guess so. Okay, we announced regarding, yes, you can see that we also announced here that we are going to, I mean, deliver a talk in the Formula Palace. So similarly, it has videos, recent videos, and useful technical articles which can be used for your projects. Okay, so with that, we'll just move to the Gather platform, and if you have any queries, you can reach out to us at racinglaunch@mathworks.com. So